Recording. Excellent. Right, so last time we were talking about how to calculate work. We're going to continue talking about work and energy, but we're going to specialize just a little bit. So first, let's talk about work contributions of individual forces. So the idea here is that this, by considering how individual forces, not the yes, I'll get to that in a minute, Sethu. By considering how individual forces contribute to the total work rather than just how the net force contributes to the total work, we can simplify problems. That's the whole reason why this whole work business is useful at all. For example, recall that F net is F1 plus F2 plus F3, and so on, right? It's just, F net is just the sum of all, the vector sum of all the different forces. And so if we still have to compute the net force, then it's kind of a waste of time, right? It's kind of a waste of time to compute the work because you've already figured out what the net force is. However, this whole business of energy and work can be useful because of the following statement. The total work from A to B, this is just the definition, is the integral from A to B of F net dot dl. But we can rewrite that using what we know about F net. That's just a sum. F1 plus F2, and so on, dot dl. Let me just back up for a second and answer Sethu's question. I believe we're in like section, let me double check. I believe we're like early in section 3, probably section 3.1 or 3.2. We're going to get to the end of 3.3 today though. Right, anyway. So we can write the total work as the dot product of the sum of all of the forces. And you guys know that integrals can be broken up additively. Come on, scroll please. Scroll please. There we go. So this is the same as the integral from A to B of F1 dot dl plus the integral from A to B of F2 dot dl, and so on. And so we can write this as work 1 plus work 2 plus work 3, and so on. The idea here is that you can consider how much work is actually contributed from each individual force. So if, say, the ith force, maybe I is 5, so it'd be like the 5th force. Just suppose one of the forces is always perpendicular to the motion, then we can ignore that force because Fi then dot dl is 0. That's what it means for two vectors to be perpendicular. If the force is perpendicular to the motion and dl points in the direction of the motion, that means that their dot product is 0. And that therefore implies that the work that you get from that force is 0. So it means that we can greatly reduce the number of forces we have to consider when we compute work. For example, if half of your forces are perpendicular to the motion, then you don't even have to worry about those forces at all. You only have to worry about the forces that are in the direction of motion. And I'm going to give a rather complicated example. Rather, an example that would be hard to do using Newton's laws, but is easy with with work. So let's take a block sliding in a frictionless loop-to-loop. And I'll draw a picture by what I mean of this in a minute. So let's say that we have a ramp, and then at the bottom, we have a circle that the block can, go through. So the block starts off up here, slides down, slides up the ramp, goes around, comes back down, comes out, and so on, right? So oh no. Undo. There we go. So you might ask, what is the difference in height between the starting and the initial, or the initial and the final position of the block? Because eventually the block will, I mean, so there's more details on line integrals in the textbook that I'm going to go over because I don't have time for it. So if you are curious more about line integrals, then check in the book. You might ask, what is the difference in height between the final maximum height and the initial height, delta y? That is to say, the block is going to come to a stop eventually, and then it would fall back down. So what is the difference in height between those two the initial and final there? And if we just examine this problem, at various points along the loop, the forces are relatively complicated, right? The normal force is always changing because the normal force is always perpendicular to the surface. So probably it was a rhetorical question. The point is that the normal force is changing, and so you would have to account for that at every point point along the path. And so when you wanted to write your F net, well, it would be mg, say, minus mg in the j hat direction plus some normal force, but you'd have to figure out what that normal force is. However, because we can break up the work done by each force into different parts, we can just look at the work done by gravity and the work done by the normal force. And note that the normal force here is always perpendicular to the velocity vector, meaning that it's always perpendicular to the path. That's always true because that's just what the normal force does. It's always perpendicular to the surface on which the object is resting. So what that means is that it means that n dot dl dt is 0, which implies that n dot dl is 0. So when we go and we plug it into the work, we would automatically find that the work from the normal force from A to B, let's say this is A and this is B, is just 0, because we can compute that work by taking the dot product, and if the dot product is 0, the integral of 0 is 0. And so what we find then is we find that the total work from A to B is the integral from A to B of n minus mg j dot dl, which is equal to minus mg, again, because n dot dl is 0. I should write that there. This is just minus mg times the integral from A to B of j dot dl. All I did was I dropped the n dot dl because I distributed, and then I factored out negative mg. And so now we're just left with the question, what is this quantity here? So consider what it means. The j dot dl, well, if dl is the path, j dot dl tells you how much vertically that path travels. So yeah, the mg is negative because it's pointing downwards. I've chosen my coordinate system to be the standard one. J dot dl, let's say that we have some path vector. Oh, it froze again. Come on. Let's say we have some path, let's say dl is this vector, just an infinitesimal vector. Well, j dot dl is the height of that vector. It's this length is j dot dl. dl is the infinitesimal vector that tells you what direction the path is going in. So an example of a dl would be these guys all along the path, and notice how their direction changes, but they're supposed to have infinitesimal length. Right, so j dot dl is basically dy. It's how much the infinitesimal vector goes vertically. And so what this j dot dl is it's just dy. And so all we have to do now is we just consider that this is equal to minus mg of ya to yb of dy. And so that gives us minus mg of yb minus ya. So that tells us that if we know, that tells us how much work is done by gravity between points A and B. This is just minus mg delta y. So the n drops out because it's perpendicular to the path. The normal force isn't 0. It's just the dot product with the path vector dl is 0. So basically, what this is not quite. I mean, we'll get there, Sonny. We'll get there. It's very closely related to the potential energy. So the takeaway here is that we can figure out how much work is done, even if we don't know what all of the forces are, because some of the forces might not contribute to the work. And so if we can learn things about the work, then we can learn things about the change in speed. Good question, Cody. The reason why so A and B are just positions, and YA and YB are the vertical positions, or are the vertical coordinates of those positions, because we're only looking at the vertical component, the dy, because we are dotting j with dl. Right. So this lens, oh golly gee willikers, it froze again. You know, you'd think that a tablet that was not, well, I guess the tablet's 5 years old, but it should be able to it should be able to record no problem. So how's everything going? I hope everything's not so hard. There we go, we're back. Okay, don't bother answering that question, it'll make me feel bad. Right, so this easily leads us to the idea of a conservative force. So gravity here is indeed a conservative force. So let's back up a little bit, and let's think about how I got that this integral worked out to be, that should actually be a delta y, because it's the integral of dy. So I briefly went over that, but j dot dl is the projection of dl. Remember that projection means, or that the dot product just means the projection of one vector along another vector. It's the projection of dl in the vertical direction. And in particular, we can draw this again. If this is dl blown up infinitely, and this angle is theta, say, then j dot dl is just dl times cosine of theta. And so we could write out this integral. By the way, I'm just doing this in more detail because I know that people have trouble with this. We could write out this integral in a more complicated manner. This is equal to dl times cosine of theta 1 plus dl times cosine of theta 2. Because notice that the length of the vector doesn't change, by the way, but the angle might change as the path, you know, travels along some other, as the path travels along some trajectory. And so what, and you know, this is an integral, so you'd have an infinite number of these. But dl of cosine of theta 1 is just equal to the height gained or lost by that small step. And so all we're doing is we're adding up the height at each tiny step, and that contributes to and that indicates to us that the sum of all of them would be the total height change. So the point here is, and perhaps it's quite remarkable, is that even though there was some complicated path with a loop-de-doo, the work done by gravity doesn't care about the path that was taken. It only cares about the initial and final positions. And that's an important fact. So not all forces will have that property where the work done by them only cares about the initial and final positions. In fact, we can categorize forces into two types. Those which do have this property, where the work done only depends on the initial and final positions, and those forces which do not have that property. So the forces that have this property are called conservative forces. So this whole business of conservative forces has nothing to do with politics, even though somebody always tries to make a joke about that every year. They're just contrasted with non-conservative forces. And the reason why we call them conservative forces is because they have something to do with energy conservation. There is a weird consequence of forces that are conservative, though. That is, if an object takes a path, perhaps I should write this down. If an object takes a path that starts and ends at the same place, regardless of the path taken, like it could go around in a loop or 8 loops or 38 loops, conservative forces don't do any work. They do 0 work. The idea here is that look back at this example, right? If we had had this loop go back around and come back to the same place, well, then the change in height would have been 0. And it turns out that because the conservative forces always have this property where they depend only on the initial and final position, if the initial and final position are the same, there's just no there's just no work to be done. Because it's easiest to think about it this way. If it's true that it doesn't depend on the path, and it only depends on the initial and final condition, you could just, the initial and final position, consider how much work is done by not moving at all. Well, if there's no motion, that means that the path has length 0, meaning that there is no work. But that has the same initial and final position as starting from a point and then going around a big loop and then coming back to that point. So if it only depends on the initial and final position, it does the same amount of work as not moving at all, and that is 0. And so it's a nifty consequence of conservative forces, that they have this property. That's not how you spell conservative. Conservative, there you go. The work done by conservative forces from a point A to the same point is just this, and I'll explain what these symbols mean in a minute, .dl, which is 0. This circle through the integral just means a closed path. And when I say closed, what I mean is that the path rejoins back with itself. Think of like a circle or like a figure 8. All of those are closed paths because they don't have endpoints. So, by the way, we can show this fairly explicitly, but with an example. Let's say we have a ball thrown upwards and then caught at the same height. So take a ball, throw it upwards, you catch it at the exact same height. So the work done by gravity, say from the hand to the hand, that's not a D, is the same, I mean, work is additive, it's the same as the work done by the gravity from the hand to the air, i.e. maybe to its peak height or something, plus the work done from the air to the hand. So gravity does work on its way up and it does work on the way down. So we can do these integrals though. This is the integral from, say, the hand to the air. Remember, A is always at the bottom, B is always at the top. The force is minus mg in the j hat direction, dotted with dy j hat. In this case, it's because the hand is, or the ball is going upwards, so the path vector, dl, is equal to dy j hat. So that would be the first term. And then we add to it the integral from the air to the hand. And we have the same force, minus mg j hat, dot, and this time we have a minus dy j hat, because the path is going down. And so we can just do this integral. So mg we can factor out, and then it's j dot j, which is 1. So this is just an integral of dy from the height at the hand to the height in the air. So that's just delta y. And then over here we have plus minus mg again. We have a minus dy, and then we have a, we have a minus delta y here. Because this is the dy from, or, well, it's the dy from the, we have a minus sign there. And so you end up with 0. And you could work this out more explicitly if you really wanted to, but it's just a matter of being, perhaps being precise. This should actually be a plus here. There's an issue regarding the coordinate system that I've chosen. This is with regard to height, basically. Yeah, so that should actually be a plus, but the path goes backwards. So I could have done it either way. I fudged and I made a mistake and had an extra negative sign. But I mean, you could have done this integral explicitly with numbers, and you would have seen it work out. But the idea here is just that the path is going in the y direction, but it's going backwards. So you have to choose one of those negative signs. You can't have both. The whole point, though, is just that when throwing the ball up, the delta y is positive because it ends at a higher height. When throwing the ball up, the gravity is doing negative work because we have a minus sign here. And then when throwing the ball down, gravity is doing positive work. And so the idea is just that the amount of work that the gravity does is constant, or is 0, because we're ending and starting at the same height. I mean, we're doing the integrals with respect to y. Just imagine that we have y air and y hand. That's all. I was just being a little bit sloppy. But hopefully it's not so surprising that the work done by gravity, if you throw a ball up in the air, is going to should be 0. And the reason it should be 0 is because it should have the same speed coming down as it had going up. And you guys all experience that. If you throw a ball up really high, you launched it with a very high speed, it'll hit your hand at a very high speed. If you just lightly toss it, hell, I have a ball here. Demonstration. If I just toss it a little bit, it doesn't hit my hand very quickly. If I toss it significantly more, it'll hit my hand significantly harder. And that's just because the speed is higher when it's coming down. And the speed that it leaves my hand with is the same that it hits my hand with, meaning that no work must have been done. I'm going to give another example of a conservative force. The elastic force is conservative. Remember, the elastic force is the force due to springs. Yes, yeah, Cody, that's precisely it. It does precisely apply to the loop-de-loop. As long as it is whatever speed it had initially, at the same height, it will have that same speed. So the elastic force is conservative. Let's recall Hooke's law. That's a description, or a mathematical description of the elastic force. That is that the elastic force is negative k delta x, where delta x is the position of the object minus the equilibrium position of the spring. So this is like x minus x equilibrium. Maybe you want to use an r there, but people tend to use x. So let's compute the work done by a spring on a block as the spring is compressed. So draw a picture of the before. So we have our spring, we have our block. And let's say that, let me draw this out a little bit further. Let's say that this distance here, this is, say, x equals 0, just because we need a coordinate system, and we're not going to worry about xa. or sorry, we're not going to worry about the y-axis because this is a one-dimensional problem. And let's say we look at this right-hand end, we call this xa, that position. Then we have after, and it's compressed a little bit. So we have, again, look at the right end, we have xb over here. xa would have been somewhere over here. I'll draw it as like a little ghost block. That's xa, and then we have, oh, I might need a new machine. Maybe I'll close out of Chrome, maybe that'll speed it up. Golly gee willikers is right. Yes, I'm actually a cartoon from the 1950s. Maybe it would be easier if I just, no. Maybe I should invest in a blackboard though. So then I can just record it. Ah, okay, we're back. So this point over here is going to be x naught, or x equals 0. Again, it's just a coordinate choice. So let's compute the work done by the spring. Oh, no, we're not back. I don't think I can add you on Steam. I think that that's like against the rules. Hey, don't judge. There we go. Okay. Anyway, so let's compute the work done by the spring. This is the elastic, the work done by the elastic force from A to B. So that is the integral from A to B of F spring dot dl. Now, by the way, notice that I've indicated that I know nothing about the, oh, let's just say that x equals 0 is where the equilibrium is, just for example. We could have chosen it to, we could have labeled it anything else and it would have canceled out, but let's just take that as an example. So this integral then, well, the force is, in one dimension, is just explicitly minus k x, because x equilibrium is just the number 0. So in this case, we have the integral from A to B, or let's actually be more explicit, from xa to xb of negative k x in the I hat direction, because x goes from, or x, the vector x is this vector here, and it's this vector here, right? That's xa, this is xb. And so if we have negative k times that vector, then it's negative k times x in the I hat direction, dotted into dx I hat. So that's equal to negative k times the integral from xa to xb of x dx. You guys know how to do this integral. So what we get is we get negative 1/2 kxb squared minus 1/2 kxa squared, which is just negative 1/2 k, and I'm going to be very careful with parentheses here. It is delta of x squared. So note again that I actually didn't tell you if the spring went back and then forth and then back and then forth again, or if it just went straight from A to B, or if it went backwards and then straight to and then to B. The point is the path didn't matter. The only thing that mattered was the change in the position, basically. In this case, it's the square of the change in the position. Sorry, the change of the square of the position. You have to be careful there. The result isn't identical to the gravity case. There, it was just it just depended on delta y and not delta y squared, but and not delta x squared. But the idea is still it only depends on where the endpoints are. So it's relatively it should be relatively easy to see why this only depends, or why this round trip criterion is satisfied. I.e., if you start and end at the same place while attached to a spring, then the spring force will have done no work, because if your initial place was at 5 centimeters from equilibrium and your final place is 5 centimeters from equilibrium, then delta of 5 centimeters squared minus 5 centimeters squared, that's still just 0. It'll give you 0 work. Now, that's great, but not all forces are conservative. For example, kinetic friction is not conservative. So let's take a simple case. Sorry, it looks like somebody may have slapped the keyboard. The simple case is that blocks sliding around back and forth on a rough surface. So let's say that you are that here's position A, here's position B. Let's say initially you go from A to B, and then you go from B to A. And let's say this is plus X. That's the plus X direction. We're just imagining a block moving from A to B and then backwards from B to A. So when moving right, well, kinetic friction always opposes the sliding motion. So in that case, the kinetic friction force is negative mu k n in the I hat direction. And when moving left, the kinetic frictional force is positive mu k n I hat. It's the frictional force is pointing to the right. Oh, it actually looks like we are going to finish on time. I actually might not even have enough stuff for today to finish. So, well, yeah, I can add some more questions then. So now let's compute the total work. And by the way, n is just a constant here because we're assuming you're not pressing down harder or lighter on the thing, and gravity's fixed. So the total work done is the work done from A to B plus the work done from B to A. Let's call this XA and this XB, just to give them names. So this is the integral from XA to XB of negative mu k n in the I hat direction, dotted into dx I hat, plus the integral from XB to XA, mu k n I hat, dotted into dx I hat. Let's make that d better. The direction of the path is accounted for in the bounds here, and that's why I don't have a minus sign under this dx. I could have had a minus under that dx, but then I would have needed to flip the bounds because I would have to redefine my coordinate system. Anyway, neither here nor there. So we do this computation. The I dot I is 1, and so we get negative mu k n times xb minus xa plus, mu k n times xa minus xb. Why is it negative going right? Oh, the work done by the friction is negative. Well, it's not necessarily it's not necessarily negative. Well, okay, yes, I suppose of course it's negative, and that's because it's causing a reduction in the speed. And so what we glean from this is that this is negative 2 times mu k n xb minus xa. But importantly, this is not 0, right? The idea here is, and so what we've concluded then is that the integral of fk dot dl is over a closed path it's just not 0. And so this is an example of a non-conservative force, i.e. we found a force that even if you end back where you started, there's still work being done. So in cases where you have non-conservative forces, the path matters. And that's an important point. You can't just worry about the initial and final position whenever you have any sort of non-conservative force. And non-conservative forces are, I don't want to say they're relatively common, but all frictions and drags are non-conservative. And so they will show up in that form pretty regularly. Right, so we're going to change gears a bit. I am going to run out of stuff to say, so I'll ask for questions after I'm done. But we're going to talk about power. Unlimited power. So this is just another term that's worth introducing. The idea here is that forces can change the total energy of the system, of a system. This is a la the work energy theorem. So remember that kinetic energy is part of the energy of the system. And so if a force can change it, what is the sign before F sub k dot dl? That just indicates what direction the force is in. In this case, the force was pointing to the left because the object was moving to the right, and that's what friction does. It points opposite the direction of motion. In this case, when the object's moving to the left, the force is pointing to the right, and so that sign accounts for that. All right, back to power. So the idea here is that if forces can change, if forces affect the change in the kinetic energy of a system, i.e. the work done by a force is equal to the change in the kinetic energy, then, I mean, it's quite obvious then that forces change the total energy of the system. And so what power does is power measures how fast, that is not on the line. Power measures how fast or how quickly that energy transfer occurs. Now, you guys all are familiar with, like, or you've at least all heard of conservation of energy. And so when I say energy transfer, what I mean is that the force is giving the system more energy or taking energy away from that system. We haven't actually talked about energy conservation yet, but we will get there. And so formally, we can define power. Power, given by a capital P, is the time derivative of work done. And the units of power, remember that the units of energy or work are joules, so the units of power is a joule per second, also known as a watt. What is it known as? Watt isn't a stupid joke. And so just like how we can isolate the work done by individual forces, like how we can only consider the gravitational force, for example, here we didn't have to worry about the normal force. What we can also do is we can isolate, or we can measure the power delivered by various forces. So we can see how much power does gravity deliver, how much power does the normal force deliver, and so on. Just like with work. And so let's just take an example here. Consider cruising in a car. Like you have your cruise control turned on, and you're just cruising along. In that case, delta KE, i.e. the change in your kinetic energy, which depends only on your speed and your mass, of course, that's 0 because your speed isn't changing and obviously your mass isn't changing. So that means that the work done by all the net forces, the total work done is 0, i.e. the power or the total power is 0. But it's not like you're not expending any energy to do any of this, right? Like that's just not the case. There is some, like your car has some power. It's driving its engine with some horsepower. So if we want to actually answer the question, how much horsepower does your car have, meaning at what rate can it transfer energy from gasoline to your wheels, you have to isolate the different forces. So the idea here is that we can compute the power delivered by the engine alone, just by figuring out what forces or what force the engine is providing. So there's a nifty little shortcut for computing power that comes up fairly regularly, and it applies in Nope. Oh, there we go. Well, may as well take a drink. Yeah, I would do this whole take a shot every time my PC freezes, but I think by the end of lecture, we'd be smashed. And you guys probably can't legally drink, so let's not do that. And if I did that, I probably wouldn't be able to get through for my meeting that's in, 15 minutes. So Arizona, I'm not a shill, but Arizona green tea is amazing. Okay, it's back. Right. So there's a nice shortcut for computing power. Oh, nope, it's not back. What do you mean there's no juice in that can? I mean, of course there's no real juice in that can. But, like, there's still stuff in it. Yeah. If only I was getting sponsored by Arizona, right? I mean, like, you can hear it. Right? Like, I promise I'm drinking something. All right, let's try again. All right, so if I say the word nice, will it freeze again? No, okay, so there's a nice shortcut for computing power. And again, this isn't always true, but it is well, it's approximately true anyway. So the power is the rate of change of the work done, right? I think we can all agree on that. I'm from Arizona, by the way, so it's extra funny to me, even though Arizona green tea is not made in Arizona. And so what does dW actually mean? So dW is just the d of an integral, f dot dl. And the whole point here is that you guys know that, like, if you take the derivative of an integral, you just get the thing back again. So the d of this integral is really just f net dot dl. And so what we can say is that this is d of f, sorry, this is just f dot dl dt. And dl dt, well, we know what that is. That's just the velocity. So this is just f dot v. Let me get rid of this. So this is an easy way to calculate the power if you know the force and the velocity vector. You just take the dot product of the two, and that'll give you the power. So if you wanted to figure out what the a good example would be, let's say you know your car has is a 100 horsepower like buggy or something, right? So it takes like all of your car's power to actually just coast at 80 miles an hour. So if you wanted to figure out what your how much force your engine is actually exerting in pushing you along the road, what you could do is you could say 100 horsepower, it's not an SI unit, but you could convert it to 100 SI unit, is equal to F dot V. And you plug in what V is. Let's say that you're moving in such and such a direction at 80 miles an hour. So this would be Fx, say the force in the direction you're traveling, let's call it F sub V actually, times 80 miles an hour. And again, not an SI unit, but you could convert it. So you could explicitly calculate how much force your engine is providing in the direction of motion. Now, it's obviously not providing all of its force in the direction of motion because there's inefficiencies everywhere. But this would give you a good estimate for how much force your engine can actually provide. Anyway, so that's all the material I have for today. I thought I had more. I didn't think I would make it through, but that is everything I have. So, and we'll continue again next week. But since we have 5 minutes or so, why not I open this up to questions? So questions about this stuff anyway, not about my product placement. Right, so line integrals. So one of the reasons I didn't go through line integrals is because I explicitly don't want to worry about the mathematics of it, because you guys have all taken math and all that business. However, what I can do is I can just briefly explain what the whole dealio is. A line integral is basically just an integral along something that's not a straight line. Can I explain the General Kenobi? What? What General Kenobi? What about him? Anyway, so let's take your normal integral, right? Your normal integral, if you have some function that looks like this, how do you actually compute your integral? Let's say this is f and this is x. So if you wanted to compute f of x dx, what does that actually mean? Well, it means that you draw a whole bunch of boxes here. You guys have seen these. These are called Riemann sums. Draw a whole bunch of boxes and so on, and you add up their area underneath each of the boxes. The sign before the fk.dl. Yeah, here, this thing. Yeah, the circle thing. Yeah, it just means it's a closed path. Just means you go back to where all it is it's just extra notation that tells you something special about that path. But anyway, let's go back to talking about line integrals because I think you guys could probably use this anyway. So you guys know how the integral is just a limit process of adding up the area of all of these rectangles, right? You find the area of the rectangle, and then you find that area, whatever. And then you take the limit as the rectangles get narrower and narrower until you have so many rectangles that that's not an approximation anymore. And then these rectangles now become infinitesimally thin. You multiply the height of the rectangle by the width of the rectangle, that gives you the area, and then you add up all those infinite number of rectangles. So really, what this symbol means is the little curly s thing is sum, and then it says sum up f of x, the height of the rectangle, times the width of that rectangle, and then add them all up. So f of x times dx is an area, dx is the width, and f of x is the height. So all a line integral is doing is, let's say that we have some two-dimensional path. Let's say this is f of x and y. And let's say that you start, I'm going to try to draw this in 3D, but it'll be kind of hard. You start there, and say you end here. And let's say your path wiggles around. So like maybe it takes this wiggly path through space or something. Yes, sometimes you will. The idea here is now all you're doing is you're just adding up these areas. And so those areas, those areas will depend. So this would be a path integral along some path. Those areas would depend on the width and on the height at that value. So in our context, our path integrals look something like, let's do f dot dl. So how can we rewrite that? Well, the width of our integral would be effectively, so let me rewrite this. You guys know how to write the dot product in terms of the product of magnitudes, right? So this is just equal to f, the magnitude of f times the magnitude of dl times cosine theta. And so we can rearrange that to just be f times cosine of theta times the magnitude of dl. And then the magnitude of dl, that is the width of our rectangle. And then the height of a rectangle is the magnitude of f times cosine of theta. And then you're just adding up those rectangles there. So in our situation, the way we describe dl is we say, look, let's say dl is pointing at a 30-degree angle, right? Well, we know that yeah, so how do I want to, let's how do I want to phrase this? So there's something to be said about the magnitude of dl relative to dx and dy, and so approaching it with a 30-degree angle makes it trickier, and I don't want to go into that. So instead, let's just worry about a 45-degree angle because that's more straightforward. Let's say you have a 45-degree angle. then what we would say is that the path that you travel is dx in the I hat direction, and then dy in the j hat direction. And by the way, when I say the magnitude, what I'm now saying is that our magnitude should be dx squared plus dy squared, which is what we want it to be. But at a 30-degree angle, you have to worry about sines and cosines and so on and so forth. So the whole takeaway is just that you would just, in this case, dl is just the vector dx I hat plus dy j hat, and that's it. So then you would take this, you would dot it into your force vector, and then you would just do the integral. And there might be two integrals. You might have, it might be like f of x dx plus the integral of f of y dy, and that's okay. This would be from ya to yb. This would be from xa to xb. And that whole thing is like the integral from a to b of f dot dl. That's how you would handle it in this case. So traditionally, and you could figure it out using the slopes. This whole argument, like if this was a 30-degree angle, you could describe this line y equals mx plus b, and then what you could do is you could then just say that dy should be m dx, and so you would have that your dy is, well, yeah, that would be enough. And so your dl, whatever that m is, your dl would just be, for example, it would be dx in the I hat direction plus m dx in the j hat direction. Because this is the amount that your y vector, or that your vector raises in the vertical direction as a function of the horizontal direction. And by the way, he goes into detail on this in the textbook. This is in section 3.1, I think. But that's all I'm going to say on it. In most of these cases, it's just going to be a matter of writing the path as, the path will be fairly straightforward. It'll either be a straight line or well, it'll always be a straight line, I think. I can't imagine I'll give you a harder problem than that. Anyway, I'm going to call it there because I do have a meeting in like -3 minutes. So I'm going to stop recording, and I will